Good morning, class. Today I'm going to talk to you about impulse and momentum. Okay, so these are these two words, impulse and momentum. I think I'll talk about momentum first because I think momentum is an easier concept to understand. So, momentum. Well, momentum is expressed as, in our book anyway, as a P. Okay, momentum is P. And we say that, let me just move this over. Momentum P equals mass times velocity. But what is momentum? What do we think of as momentum? You've probably heard of momentum before. So momentum is like, it's a little bit like inertia, only it's when something is moving really fast and it's really heavy, you say it has a lot of momentum. It's hard to stop something that has a lot of momentum. For instance, if a car is rolling towards you at 10 miles an hour, if you try to stop it just by your own body, you'd find it was very hard to stop because it has so much momentum. Because it's not just how fast it's going, it's how heavy it is, how much mass it has. So momentum is mass times velocity. And so let's see, the unit for that is going to be, the unit is kilogram meters per second, right? Mass times velocity. Let me try that. Let me get rid of, actually I'm going to pause, go back to this thing so I can do that easily. Okay, so for instance, let's say you have a, a person running. Okay, so maybe the person weighs, their mass equals 50 kilograms, okay, and let's say their velocity is equal to, not 10, hold on. How about velocity equals 5 meters per second. So we would say that their momentum is the mass times velocity, that's 50 times 5, which is 250 kilogram meters per second. Okay, that's kilometers per second. Hold on a minute. Okay, there we go. Kilogram meters per second. I'm going to get the hang of this program sooner or later. Okay, let's put that away. So that's momentum. Mass times velocity. It's pretty straightforward. It actually is a vector like velocity. It has a direction. There's positive momentum, negative momentum. Momentum can have at an angle. It can have a particular direction, just like velocity. Okay, now impulse is a little bit trickier. Impulse, okay, let me just write down here, impulse, okay, now impulse, we use a J for impulse, okay, impulse is equal to force times change in time. Okay, now that's close to true. Actually, usually when we talk about impulse, we're talking about average force. So I'm going to put a little line over the force. Hold on, I got to pause for a second. So I just left for a second. I'm back now. So yes, impulse is force times change in time. So let's see, that unit is going to be basically Newton seconds. See how that comes out. Yep, that's good. what's really, so the idea of impulse is that it's kind of like, you imagine, it's usually about like when, say, something hits something really fast, like a collision, or something bounces off the ground. A typical impulse problem might be a baseball bat hitting the ball. So what you have is you have a very high average force over a very, very short period of time. And what's important is the impulse, the actual, the average force times how long that force is exerted for. And what happens is something called the impulse momentum theorem, I believe it's called. So, let me write that down, the impulse momentum theorem. Impulse momentum, O-R-E-M. See if you get that. Not too bad. Hold on and pause this. So what this theorem basically says is that the impulse is equal to the change in momentum. Okay, so what we're saying is that J equals delta T. See how that comes out. Okay, so that's impulse is change in momentum. So that's like saying that, let's see, so we've got J, which is F delta T. F delta T is equal to, okay, mass times velocity final minus mass times velocity initial, right? That's the change in momentum. So we have mass times velocity final minus mass times velocity initial. Okay, so the impulse, the force times the change in time, is the mass times the final velocity minus the mass times the initial velocity. So we can solve a bunch of problems now based on this. So basically, what you're saying is that typically what happens is something is traveling with a lot of momentum, right? It smacks into something and there's a force, maybe a very large force over a short amount of time. That thing bounces back, right? Now the momentum has changed, right? It's changed because it's all that force and all that velocity was going in one direction. Now it's going another direction. So I'm going to pause for a minute. Okay, I'm back again. So the idea here is that on the left side of the equation you've got force times time, and on the right side you have change in momentum. So if you have a lot of force for a short time, or a little bit of force for a long time, you'll have the same amount of change in the momentum. And momentum is big either if something's heavy or if it's moving fast. Obviously, you're not going to change the mass, so it's the velocity that's going to change due to this force over a certain amount of time. So let's see, I'm going to go to a new page. Actually, let me copy a couple of things and then bring them over to a new page. Okay, let's see. Copy, new page, paste. And we are going to do a problem from the book. So you might want to pause it and go get your book if you don't have it with you. And what we're going to do is we're going to example 1 on page 197. Okay? Let's see. Example 1, page 197. Okay, so we're going to go through this problem. Remember that when this is going to be your regular assignment to watch these videos, I'm going to expect to see notes. So you're going to take notes when we're solving problems, and also just general take notes from the video. You can pause it whenever you want if you have to take a note. So let's see, example 1 on page 197. I'm going to sort of write down what's in this example as we go. So we've got a baseball, mass 0.14 kilograms. So let's write that. mass 0.14 kilograms. Okay, has an initial velocity v0 equals negative 38 meters per second. Okay, v0 equals negative 38 meters per second. All right, let me move that over a little bit. As it approaches a bat, we have chosen the direction of approach as the negative direction. The bat applies an average force that is much larger than the weight of the ball, and the ball departs from the bat with a final velocity v final equals positive 58 meters per second. Okay. V final equals 58 meters per second. So the ball has changed direction. Say it started out going to the left, now it's going to the right. Let me pause this for. Okay, that's better. So, A, determine the impulse applied to the ball by the bat. Okay, so impulse. That is, let's see, impulse J equals F delta T. Okay, so let's see. We know it's also equal to change momentum, right? So it's also equal to mv final minus mv initial. And we know all those things. We know m, we know v final, we know v initial. So we can say for part A, hold on a minute, we've got J equal to 0.14 times 58 minus, hold on a minute. Okay, minus, now let's look at this. We've got M, which is 0.14, times negative 38. Okay, so let me get out my calculator here. And this is tricky because what you can see you're really ending up with is subtracting a negative, right? This is this 0.14 times negative 38. That's a negative number. So we're subtracting a negative number. That's just like adding a positive number. So let's see. 0.14 times 58. We just put it in just like it says. Minus 0.14 times negative 38. I get 13.44. So that's going to be equal to, we'll call it, well, I'll just call it 13. 13 Newton seconds. All right, that's my impulse. Okay, let's look at B. Determine the impulse, B. Assuming that the time of contact is 1.6 times 10 to the negative 3 seconds. Okay, so let me write this down. Delta T is equal to, hold on a minute. (1.6) times 10 to the negative 3 seconds. Okay, find the average force exerted on a ball. So J equals F delta T, where F is the average force. So for B, we're going to have J, which is 13, is going to equal the force multiplied by 1.6 times 10 to the negative 3. Let me just fix. Okay, so let's see. That means that F equals 13 divided by 1.6 times 10 to the negative third. Okay, so we can figure out what that equals. Let me try that on my calculator. 13 divided by 1.6 EE negative 3. 8,125. I'll call it 8,100 newtons. Okay, so let's see. That's 8,100 newtons. It seems like a lot, doesn't it? So yeah, the average force of a bat hitting a ball is actually a very high force. And that's because it's done over such a short period of time that in order to get enough impulse to change the momentum of that ball, that force has got to be very large. I noticed the book got a slightly different number, but I think what they did was they left it at 13.4, and that's why. So here, let's go ahead and give you a problem to try. All right, let me write this one out. Okay, let's imagine that we have a 0.5 kilogram basketball bounces off of the floor hold on a minute. Assume there's a period there. Okay, so what happens? Its initial velocity is negative 10 meters per second. That is, it's going down. Oh, that didn't work out so well. Hold on a minute. Negative 10. Okay. Let's see. It hits the floor. And bounces back up. At 8 meters per second. Okay, so if the ball is in contact with the floor for 0.1 seconds, what is the average force on the ball? Okay, so let's pause it and go ahead and see if you can come up with an answer. Okay, let's see. I'm going to try solving it, see if I get what you got. So I know that the impulse J is equal to F delta T. Okay, and I know that it's also equal to mv final minus mv initial. Okay, so let's see what we know here. We know that m equals 0.5 kilograms. We know that, let's see, what else do we have? We've got V initial is negative 10 meters per second. We know that V final is 8 meters per second. And finally, we know that delta T is 0.1 seconds, right? Delta T equals 0.1 seconds. All right, just cleaned up some of those. Whoops, there's one I missed. Okay, so let's see. We're trying to find the force, F. We know that F delta T equals mv final minus mv initial. Okay, so F times 0.1 equals 0.5 times 8 minus 0.5 times negative 10. So let's see, let me just do this in my calculator quickly. .5 times 8 minus 0.5 times negative 10 is 9. So F times 0.1 equals 9. Therefore, F equals 9 divided by 0.1. F equals 9 divided by 0.1, which would be 90 newtons. So the average force on the basketball is 90 newtons. So let's look how we set these up. Typically, you've got something moving initially in one direction. Finally, it's moving maybe with a different velocity, often in a different direction, but it might just be slowed down. And the change of the final velocity times the mass minus the initial velocity minus the mass is just equal to the force times the amount of time that the force is applied, the average force. So you've given a bunch of these values and you solve for the one you don't know. In this case, F. Sometimes you might be asked for F or M, and that's about it. So now in class I'll give you some problems to do from the book so you can practice this stuff. I'll see you then. Bye.